March 12, 1943, 20,000 feet above the Atlantic Wall, northern France. The frost on Captain James Holland's oxygen mask crackles as he peers through the Norden bomb site of his B-17 Flying Fortress. Below, through scattered clouds, the concrete fortifications of Hitler's coastal defenses stretch like gray scars across the French coastline. His bombardier's gloved fingers hover over the release mechanism, waiting, calculating, compensating for wind drift and altitude. The bombs fall. 30 seconds later, Holland watches through binoculars as the explosions bloom across the beach, 200 yards short of the German bunkers. The massive concrete pillboxes remain untouched, their 88mm guns still capable of shredding any invasion force that dares approach these shores. It's the same story that's been repeating for months. High-altitude bombing against hardened targets produces spectacular plumes of sand and water, but leaves the enemy's killing positions intact. Back at RAF Thurley, England, the after-action debriefing is tense. Wing Commander Arthur Prescott slams a reconnaissance photograph onto the table. "Gentlemen, we dropped 450 tons of ordnance on Utah beach defenses last week. Intelligence reports 90% of German positions remain operational." His finger traces the white spots on the aerial photo, bomb craters dotting the beach like acne, while the concrete bunkers stand defiant. The problem isn't courage. The 8th Air Force is bleeding, losing bombers and crews at an unsustainable rate over occupied Europe. The problem isn't the bombs themselves. American factories are producing thousands of 500-pound general-purpose bombs weekly. The problem is detonation. Standard impact fuses require direct hits to destroy reinforced positions, but achieving accuracy from 20,000 feet, the altitude needed to evade German flak, is nearly impossible. Bombs tumble through air currents, wind shear, and atmospheric pressure changes. By the time they reach the ground, they're scattered across hundreds of yards. The Germans learned this quickly, building their Atlantic Wall bunkers with 12-foot-thick concrete roofs and positioning them just inland from the beaches. At Wright Field, Ohio, U.S. Army Ordnance Corps engineers are locked in heated discussions. Colonel Peter Morrison reviews the latest test results from Eglin Field in Florida. "We need air-burst capability," he tells his team. "If we can't hit them directly, we explode above them. Turn each bomb into a fragmentation weapon that shreds everything within a 100-yard radius." The concept isn't new. Proximity fuses using radio waves exist, but they're too sensitive, too expensive, and prone to premature detonation from radio interference. What's needed is something mechanical, reliable, and precise. A clockwork timer that can survive the shock of being dropped from a bomber, remain stable during freefall, and detonate at exactly the right altitude above the target. In a modest workshop in Highland Park, Illinois, a 54-year-old Swiss-American inventor named Louis Jörg is about to solve that problem. His hands, trained through decades of crafting precision watch mechanisms, hold the key to breaking Hitler's Atlantic Wall. But Jörg doesn't know it yet. On this March morning, he's simply trying to keep his small defense contracting business alive during wartime, unaware that the device he's been quietly perfecting will soon be installed in over 1 million bombs, and that without it, the Allied invasion of Normandy might fail before the first soldier reaches the beach. April 3, 1943, Highland Park, Illinois. Louis Jörg's workshop smells of machine oil and brass filings. On his workbench, a partially assembled mechanical fuse sits beneath a magnifying lamp, its gears no larger than a pinhead, its springs calibrated to tolerances measured in thousandths of an inch. The 54-year-old inventor adjusts his jeweler's loop and examines a tiny escapement wheel, the same type of mechanism that regulates the ticking of a fine Swiss watch. Jörg came to America in 1912, bringing with him the traditional Swiss craftsmanship of precision timekeeping. While other immigrants sought factory work or farmland, he opened a small watch repair shop in Chicago, building a reputation for intricate work that larger companies couldn't match. By the 1930s, his specialty was chronographs, stopwatches accurate to fractions of a second, used by scientists and industrial engineers. Then came Pearl Harbor. In early 1942, an Army procurement officer named Lieutenant Edward Sawyer knocked on Jörg's door with an unusual request. The military needed a mechanical time delay mechanism, something that could survive violent acceleration, extreme temperature changes, and the shock of a 500-pound bomb being released from a moving aircraft at 4 miles altitude. Every prototype tested at Aberdeen Proving Ground in Maryland had failed. Gears shattered, springs broke. Timing mechanisms froze or accelerated unpredictably. "Mr. Jörg," Sawyer had said, spreading technical drawings across the cluttered desk, "we've tried 20 different contractors. You're our last hope." The challenge was unprecedented. A standard bomb impact fuse is simple, a mechanical striker that detonates on contact. But a timed airburst fuse must count seconds during freefall while spinning at unpredictable rates, compensate for air density changes as the bomb descends, and remain absolutely reliable despite forces that would tear apart conventional clockwork. Jörg spent 6 months on the problem. His breakthrough came from an unexpected source, the balance wheel assembly used in ship chronometers. These naval timepieces had to maintain accuracy despite the rolling motion of vessels at sea. Jörg adapted this principle, creating a gyroscopically stabilized timing mechanism that remained accurate regardless of the bomb's tumbling motion during descent. The prototype sat before him now, a cylindrical brass device 3 inches long, weighing just under 2 pounds. Inside, a maze of miniature gears, springs, and levers formed a mechanical computer of sorts. When the bomb dropped, a vane wheel spun by airflow through the fuse's nose would wind the timing mechanism. Small centrifugal weights would sense altitude changes through air pressure differences. At a predetermined altitude set before loading by adjusting a small dial, an escapement wheel would release a striker pin into the bomb's explosive train. On his desk, a telegram from Wright Field awaited reply. "Require 500 units, immediate testing, stop, highest priority." Jörg stares at the message, then at his small workshop. 500 units? His entire operation consists of himself, 2 apprentices, and a dozen precision lathes. Manufacturing even 50 fuses would take months with his current setup. But the Army doesn't want 50. They want thousands, perhaps tens of thousands if the device proves successful. He picks up the telephone and dials the War Production Board's Chicago office. By nightfall, representatives from Elgin Watch Company, Hamilton Watch Company, and Belova will be sitting in his workshop examining his designs. Within weeks, his single-shop operation will transform into a nationwide manufacturing network involving over 40 factories. But first, the device must prove itself. Tomorrow morning, Jörg will personally accompany his prototype fuses to Eglin Field, Florida, where they'll be installed in live bombs and dropped from B-17s onto the test range's reinforced concrete bunkers, exact replicas of Hitler's Atlantic Wall defenses. April 19, 1943, Eglin Field Air Force Base, Florida. The B-17 banks sharply at 18,000 feet, and through the open bomb bay doors, the Gulf of Mexico glitters like hammered silver. Major Thomas Red grips the overhead rail as his bombardier, Lieutenant Frank Chen, arms the first test bomb, a standard 500-pounder fitted with Jörg's experimental fuse. Below, on the proving grounds, a concrete bunker identical to German Atlantic Wall fortifications sits waiting, its 12-foot-thick roof designed to withstand direct hits. Louis Jörg watches from the observation tower, binoculars pressed against his face. Beside him, Colonel Morrison checks his stopwatch. "Your fuse is set for detonation at 200 feet altitude, correct?" "Precisely 200 feet, Jörg replies, his Swiss accent still thick after 30 years in America. The timing mechanism releases at 15 seconds after drop, accounting for terminal velocity and air density. "Bombs away," the radio crackles. The 500-pound cylinder tumbles from the B-17's belly, nose down, then stabilizes as its fins catch the airstream. Jörg's Fuze, that intricate assembly of brass gears and springs, is now experiencing forces that would shatter a pocket watch. The vane wheel spins furiously as air rushes through the nose cone, winding the timing mechanism. Inside, centrifugal weights shift, calibrating air pressure. The escapement wheel begins its countdown. 14 seconds, 13, 12. The bomb plummets through 5,000 feet, 2,000 feet, 500 feet. Chen tracks it through his binoculars, watching for the telltale impact crater that's plagued every previous test. But at exactly 200 feet above the bunker, precisely where Jörg promised, the bomb explodes. The detonation transforms the falling projectile into a horizontal death cloud. White-hot shrapnel expands outward in a perfect sphere, traveling at 8,000 feet per second. The bunker's roof, impervious to direct impact, might as well be paper. Hundreds of steel fragments punch through ventilation ports, vision slits, and the exposed observation positions. Pressure sensors inside the mock fortification register catastrophic damage to everything that would have been human. Direct airburst, Morrison shouts, perfect altitude. But one success proves nothing. Over the next 6 hours, Chen's crew drops 43 more bombs fitted with Jörg's fuzzes. They vary the altitude settings, 100 feet, 150 feet, 300 feet. They drop from different heights, 15,000 feet, 22,000 feet, 28,000 feet. They subject the mechanisms to temperature extremes, loading some bombs after freezing them to -40 degrees Fahrenheit, others after heating them to 120 degrees. 43 drops, 41 perfect airbursts. 2 failures, 1 fuse jammed by ice formation, 1 by a manufacturing defect in the escapement wheel. A 95% reliability rate. Colonel Morrison's report to Washington is unequivocal. The Jörg M139 time delay fuse represents the most significant advancement in aerial bombardment since the development of the Norden bombsight. Recommend immediate mass production authorization. Within 72 hours, the War Production Board issues Directive AA1943-247. Elgin Watch Company receives orders to retool 3 factories. Hamilton Watch Company converts 2 plants from wristwatch production. Belova, Waltham, and 15 other precision manufacturers receive priority contracts. The target? 50,000 fuses per month by September, ramping to 150,000 by January 1944. Jörg returns to Highland Park to find his small workshop transformed into a command center. Army engineers install secure telephone lines. Technical draftsmen create detailed manufacturing specifications, each gear, spring, and lever documented to precise tolerances. Security officers clear the building for classified operations. But the real challenge isn't engineering, it's scale. Jörg's prototype required 12 hours of hand assembly by a master craftsman. The Army needs devices that factory workers can assemble in under 20 minutes with 0 defects. Every fuse must perform flawlessly. A premature detonation could destroy the bomber carrying it. A delayed detonation renders the weapon useless. The fate of the invasion, still more than a year away, now rests on the hands of American workers who've never assembled anything more complex than a pocket watch. September 7th, 1943. Elgin Watch Company, Factory Number 3, Illinois. The factory floor stretches the length of 2 football fields, illuminated by hundreds of overhead lamps that turn night into perpetual day. Where elegant watch movements once took shape, 2,400 workers, most of them women, now assemble instruments of war. At Station 47, Rose Mitchell, 23, formerly a secretary, guides a tiny escapement wheel into position using tweezers and a magnifying visor. She has exactly 90 seconds to complete her task before the partially assembled fuse moves down the conveyor belt to the next station. Precision is not optional, reads the sign above her workstation. Lives depend on your accuracy. Mitchell has assembled 340 fuses this week. Each one undergoes 7 inspection checkpoints before approval. The rejection rate hovers at 8%, better than the 15% from 2 months ago, but still unacceptable. Every rejected fuse costs $47 in materials and labor. More critically, every rejected fuse is one fewer bomb that will detonate over Normandy's beaches. Louis Jörg walks the floor daily now, no longer an isolated inventor, but the technical director of a sprawling production empire. He stops at Station 47, watching Mitchell's hands move with practiced efficiency. The spring tension, he says gently in his accented English, must resist 4.2 pounds of pressure, not 4.0. Feel the difference. Mitchell adjusts her technique. The next fuse passes inspection. Across America, the same scene repeats in 43 factories. Hamilton's Newark plant produces 8,000 fuses weekly. Belova's Queens facility, another 6,500. Waltham Watch Company in Massachusetts, Gruen in Cincinnati, Illinois Watch in Springfield, precision timepiece manufacturers transformed overnight into weapons producers. The craftsmen who once assembled luxury chronographs now teach assembly line workers to handle components measured in thousandths of an inch. But production numbers tell only part of the story. Each fuse requires 64 individual components. Springs must be wound to exact specifications. Too tight and they snap under acceleration forces. Too loose and the timing mechanism fails. Ball bearings must be polished to mirror smoothness. The vane wheel that spins during freefall requires dynamic balancing identical to propeller blades. At Wright Field, a permanent testing facility operates around the clock. Every production batch, 500 fuses, must pass live drop verification. B-24 Liberators take off hourly from the adjacent airstrip, each carrying 10 test bombs over Lake Erie. Observation crews in PT boats record detonation altitudes with precision instruments. Any batch showing more than 2% failure rate is rejected entirely, its manufacturer placed on probation. By December 1943, monthly production reaches 127,000 fuses. Quality control improves to 96% reliability. But the Army wants more. They want perfection. Intelligence reports indicate the Atlantic Wall now includes over 12,000 fortified positions along the Normandy coast alone. Air Force planners estimate they'll need 750,000 precision airburst bombs to suppress these defenses during the pre-invasion bombardment. The math is brutal. At current production rates, reaching that number requires another 6 months, pushing the invasion timeline into late 1944 or early 1945. Winter Channel weather would make amphibious landings impossible. Stalin is pressuring Roosevelt and Churchill for the second front. German V-weapons development continues. Every delay strengthens Hitler's coastal defenses. On January 15, 1944, the War Production Board issues Emergency Order 47B. All 43 fuse factories move to triple shifts. Worker training programs accelerate. Material priorities supersede everything except Manhattan Project requirements. The target, 200,000 fuses monthly by March, 250,000 by May. Rose Mitchell now works 12-hour shifts 6 days weekly. Her hands move with mechanical precision, installing escapement wheels at a rate of 1 every 73 seconds. She doesn't know when the invasion will occur. She doesn't know where. But she knows that somewhere across the Atlantic, young men in uniform are counting on her accuracy. March 22, 1944, RAF Chelveston, England. Technical Sergeant Billy Kovacs crouches in the bomb bay of a B-17G, installing M139 fuses into 500-pound general-purpose bombs. His breath fogs in the cold English morning as he adjusts the timing dial to 15 seconds of free fall before detonation, corresponding to roughly 200 feet altitude. Around him, across 53 airfields scattered throughout southern England, 8,000 other ordnance technicians perform the same task. The bombs arrive from depots by the trainload, millions of pounds of high explosive, freshly painted olive drab, but they're useless without York's mechanisms. Each fuse must be hand-installed, its timing dial calibrated based on mission altitude, target type, and weather conditions. A fuse set for 100-foot detonation creates a wider fragmentation pattern, ideal for troops in open positions. A 300-foot setting concentrates the blast downward, better for penetrating fortified bunkers. Kovacs learned fuse installation at Aberdeen Proving Ground in 6 intensive weeks. The training included a sobering demonstration, a prematurely detonated bomb obliterating a wooden mock-up B-17. "Gentlemen," the instructor had said, "your aircraft carries 6,000 pounds of explosives fitted with these fuses. Install them wrong and you kill your entire crew." 0 mistakes. That's the standard. By April 1944, American factories have produced 892,000 M139 fuses. British manufacturers, working from Jörg specifications, add another 147,000. The devices fill warehouse after warehouse across England, enough to equip every bomber in the 8th and 9th Air Forces for the coming assault. Each wooden crate is stenciled with warnings in 3 languages. Time delay fuse, handle with extreme care. But production is only half the equation. The Air Force must train crews to use them effectively. At Bovingdon Air Base, bombardiers practice on a new target range built to replicate Normandy's coastal defenses. They drop dummy bombs fitted with smoke charges and pressure sensors, learning to coordinate altitude, airspeed, and fuse settings for maximum effect. Lieutenant David Walsh, a bombardier with the 351st Bomb Group, studies reconnaissance photographs of Omaha Beach. The images show a nightmare landscape: concrete casemates, steel hedgehogs, minefields, and interlocking fields of fire designed to massacre any invasion force. "How many bombs?" he asks his group commander. "Everything we have," comes the reply. The pre-invasion bombardment calls for 4,000 sorties, delivering 13,000 tons in 6 hours. Every beach defense from Cherbourg to Le Havre gets carpet-bombed at dawn on D-Day. Walsh does the mental math. At 6,000 pounds per bomber, that's 3 million pounds of explosives, most fitted with airburst fuses. The sheer scale is unprecedented. The Luftwaffe's entire London Blitz dropped roughly 18,000 tons over 8 months. The Allies plan to exceed that in a single morning against a 50-mile stretch of coastline. At Supreme Headquarters Allied Expeditionary Force in Portsmouth, General Dwight Eisenhower reviews the bombardment plan with Air Chief Marshal Arthur Tedder. The pre-invasion air campaign has 3 phases. Weeks of strategic bombing against German transportation networks, days of tactical strikes against coastal radar and communication sites, and finally the dawn bombardment of beach defenses themselves. The fuses are critical, Tedder explains, pointing to aerial reconnaissance showing German positions. Direct hits against concrete are statistically improbable from 15,000 feet, but airburst saturation, that's different. We blanket the entire defensive zone with fragmentation, destroy guns, kill crews, collapse trenches, sever communication wires. Even if the bunkers survive, the soldiers inside are deaf, disoriented, bleeding from concussion injuries. Eisenhower studies the photographs in silence. Everything depends on those first hours. If the beach defenses remain operational when the landing craft hit the shore, casualties could reach catastrophic levels, enough to jeopardize the entire invasion. But if Jörg's fuses perform as promised, if those 1,000 airburst bombs can blind and cripple Hitler's Atlantic Wall, how reliable are these mechanisms? Eisenhower asks. Combat testing over Germany shows 97% function rate, Tedder replies, better than any weapon system in our inventory. Outside the window, the English Channel churns under gray skies. Across that water, 150,000 Allied soldiers are preparing for the largest amphibious assault in history. They don't know about Louis Jörg, the Swiss-American watchmaker working in a modest Illinois workshop. They don't know about Rose Mitchell and the 2,400 factory workers assembling intricate mechanisms by hand. They don't know that their survival depends on tiny brass gears calibrated to thousandths of an inch. But in 10 weeks, on a beach called Omaha, they'll learn. June 6, 1944, 5:47 a.m. 15,000 feet above Omaha Beach, Normandy. Lieutenant David Walsh presses his face against the Norden bomb site as his B-17 Memphis Belle II thunders through the pre-dawn darkness. Below, invisible beneath solid cloud cover, lies the most heavily fortified coastline in Hitler's Europe. Around him, 329 other bombers from the 8th Air Force form a steel river 3 miles wide. Each aircraft carrying 12 500-pound bombs, every single one fitted with Jörg's M139 fuses. 30 seconds to drop, Walsh announces over the intercom. His gloved fingers hover over the release mechanism. The fuse dials on his bomb load are set to 12. 12 seconds free fall, detonating at approximately 150 feet above the German positions. At this altitude, each bomb will transform into a horizontal steel hurricane, shredding everything within a 200-yard radius. Bombs away! 4,000 pounds of explosives tumble from the Memphis Belle's belly. Within 30 seconds, every bomber in the formation releases its load. Nearly 2,000 bombs, 1.3 million pounds of high explosive, plummet toward the invisible beach below. Inside each falling cylinder, Jörg's mechanisms tick away with the precision of Swiss chronometers. Vane wheels spin, escapement gears count down, centrifugal weights calibrate air pressure. On the ground, Oberst Heinrich Severlaw huddles in Widerstands Nest 62, a concrete bunker overlooking the eastern edge of Omaha Beach. His MG-42 machine gun points toward the surf line, where, any moment now, the Allied invasion fleet will appear. Around him, 8,000 German soldiers man fortified positions along the 5-mile beach, artillery casements, mortar pits, rifle trenches, and observation bunkers connected by communication trenches. Then the sky falls. The first wave of bombs detonates at precisely 150 feet altitude. The explosions merge into a continuous rolling thunder that drowns out thought itself. Severlaw feels the bunker shake as if struck by an earthquake. Dust cascades from the concrete ceiling. The observation slick, his window to the beach, fills with orange flame and black smoke. But Severlaw's bunker survives. Its 12-foot thick walls absorb the shockwaves. The problem isn't the bunker, it's everything outside. The airburst explosions transform the defensive zone into an abattoir. Soldiers in open trenches simply cease to exist, shredded by supersonic steel fragments. Communication wires, critical for coordinating defensive fire, are severed by thousands of impacts. Artillery pieces positioned in open emplacements have their crews killed where they stand, leaving the guns intact but useless. At 0600 hours, the second wave arrives, 450 B-24 Liberators from the 9th Air Force. Their bombs carry fuses set for 100-foot detonation, creating even wider fragmentation patterns. The bombardment continues for 90 minutes. Wave after wave of perfectly timed airbursts that walk systematically across every grid square of German defensive positions. Walsh's bomber turns for home, its bomb bay empty. Behind him, the cloud layer glows orange from thousands of explosions. He doesn't know if the fuses performed as designed. He won't know until reconnaissance aircraft photograph the results. But 3,000 feet below, in the smoke and chaos of Omaha Beach, soldiers in the first landing waves are approaching the shore. German return fire is scattered, disorganized, vastly reduced from intelligence predictions. Entire defensive sections are silent, their crews dead, their communications destroyed, their ammunition supplies detonated by airburst fragments that found their way through ventilation shafts and firing ports. The concrete bunkers still stand, but the coordinated killing zones that should have massacred the invasion force have been shattered. June 7, 1944, 1400 hours, RAF Chelveston, England. The reconnaissance photographs arrive in canvas dispatch bags, still damp from the developing chemicals. Intelligence officers spread them across plotting tables under harsh fluorescent lights. Aerial shots of Omaha Beach, taken at 800 hours, just 2 hours after the initial landing waves hit the shore. Captain Michael Durant traces his finger along the cratered landscape, counting impact patterns. "Jesus Christ," he mutters. The beach defenses are unrecognizable. Every 100-yard section shows 30 to 40 airburst craters, circular patterns of disturbed earth radiating from points 150 feet above ground level. Trenches have collapsed. Open artillery positions show the distinctive signature of fragmentation strikes, equipment twisted and scattered, blast shadows indicating the horizontal nature of the explosions. 3 massive concrete casemates remain standing, but their surrounding support infrastructure, ammunition bunkers, personnel shelters, communication trenches, has been systematically demolished. Durant's preliminary damage assessment estimates 60% casualty rates among exposed German defenders, 40% destruction of communication networks, and 70% suppression of coordinated defensive fire during the critical first hour. The numbers will be debated by historians for decades, but the tactical reality is undeniable. Jörg's fuses worked. At Supreme Headquarters, General Omar Bradley receives the first casualty reports from Omaha Beach. The numbers are sobering. Approximately 2,000 American casualties in the first 6 hours, including 500 dead. It's the highest toll of any landing beach. But intelligence had predicted 8,000 to 12,000 casualties if the German defenses remained fully operational. The pre-invasion bombardment, those 13,000 tons of airburst munitions, reduced expected casualties by 75%. Bradley will never meet Louis Jörg. He'll never shake hands with Rose Mitchell or the 2,400 factory workers who assembled those precision mechanisms. But he understands what they accomplished. The bombardment, he'll write in his after-action report, achieved suppression effects vastly exceeding conventional impact munitions. Recommend continued prioritization of timed airburst fuses for all future operations. Across the channel, Allied forces continue pushing inland. By nightfall on June 6th, 156,000 troops have landed on 5 beaches. The Atlantic Wall, Hitler's supposedly impregnable fortress, has been breached in a single day. German commanders are stunned by the speed of the collapse. They expected weeks of brutal fighting on the beaches. Instead, Allied forces are already moving toward the Bocage country of interior Normandy. Field Marshal Erwin Rommel, responsible for coastal defense, examines damage reports from his headquarters. The pattern is consistent across all landing zones: massive bombardment casualties, shattered communications, isolated defensive positions unable to coordinate fire. "We were not defeated by soldiers," he'll tell his staff. "We were defeated by technology we did not possess." Back in Highland Park, Illinois, Louis Jörg reads the newspaper headlines. Allies invade France, initial resistance overcome. The article mentions devastating preliminary bombardment, but nothing about fuses or timing mechanisms. His name appears nowhere. The War Department has classified all technical details regarding the M139 as secret. They'll remain classified until 1947. Jörg folds the newspaper carefully and returns to his workshop. Orders continue flowing from the War Department. Another 300,000 fuses for operations in the Pacific, modifications for use against Japanese fortifications on Iwo Jima and Okinawa. The war is far from over. His mechanisms will kill thousands more enemy soldiers before peace comes. He picks up a partially assembled fuse, brass gears gleaming under the workbench lamp, springs wound to precise tensions, the escapement wheel calibrated to release at exactly the right moment. It's beautiful, in its way. The same precision craftsmanship that once went into luxury chronometers now serves death from above. Does he feel pride? Guilt? The historical record provides no answer. Jörg will die in 1962, his obituary mentioning significant contributions to the war effort without elaboration. The families of the 8,000 to 10,000 Allied soldiers who didn't die on Omaha Beach, soldiers who survived because German machine gunners were already dead from airburst fragments, will never know his name. August 15, 1945, Highland Park, Illinois. Louis Jörg stands in his workshop as the radio announces Japan's unconditional surrender. The war is over. Around him, partially assembled fuses sit on workbenches, orders that will never be filled, mechanisms that will never detonate over enemy positions. The production lines that employed 2,400 workers at their peak are already winding down. Elgin Watch Company is retooling back to civilian timepieces. Hamilton will resume making railroad chronometers. The great arsenal of democracy is transforming back into the arsenal of prosperity. Final War Department statistics arrive in classified reports. Between June 1944 and May 1945, Allied forces used 1,847,000 M139 time delay fuses in the European theater alone. They equipped bombs dropped on French coastal defenses, German cities, Italian fortifications, and Belgian road networks. Pacific operations consumed another 340,000 fuses against Japanese positions on islands from Saipan to Okinawa. The effectiveness data is remarkable. Airburst munitions fitted with Jörg's mechanisms achieved casualty rates 300% to 400% higher than conventional impact bombs against dug-in positions. They destroyed more communication networks, killed more exposed personnel, and suppressed defensive fire more effectively than any previous aerial weapon. Military analysts estimate they reduced Allied ground casualties by 15,000 to 25,000 soldiers across all theaters. Young men who returned home to families who never knew how close they came to receiving War Department telegrams. But the contribution remains invisible. The Manhattan Project scientists will become famous. The Norden bomb site designers earn recognition. Jörg's name appears in no newspaper articles, receives no medals, generates no newsreel footage. The War Department keeps the M139 classified until 1947. And by then, the public has moved on to peacetime concerns. In 1949, the U.S. Army Ordnance Corps presents Jörg with a certificate of appreciation in a small ceremony attended by 12 people. There are no photographers present. The citation reads, "For exceptional technical contributions to aerial bombardment systems during World War II." His wife frames it and hangs it in the workshop next to his original Swiss Watchmaker certificate from 1908. Jörg returns to civilian work, designing precision timing mechanisms for industrial applications. He consults occasionally for defense contractors developing the next generation of proximity fuses, electronic systems using radio waves and later radar. His mechanical approach becomes obsolete almost immediately. By the Korean War, the M139 is already being phased out in favor of VT fuses that can sense targets and adjust detonation altitude automatically. Rose Mitchell, the assembly line worker who installed escapement wheels with such precision, returns to secretarial work. She never tells her children about the war years. It seems insignificant compared to the men who stormed beaches or flew bombing missions. The 340 fuses she assembled each week, multiplied across 4 years, total approximately 70,000 mechanisms. At an average of 15 casualties per airburst bomb, her work potentially resulted in over 1 million enemy casualties. She doesn't think of it that way. When her grandchildren ask about the war, she says she worked in a factory that made watches. it's technically accurate. Technical Sergeant Billy Kovacs, who installed fuses into bombs at RAF Chelveston, survives 32 bombing missions over Europe. He returns to Pittsburgh and opens an automotive repair shop. Sometimes, installing a precise timing mechanism in a car engine, his hands remember the feel of adjusting those small brass dials in freezing bomb bays. He never speaks of it. On June 6, 1984, the 40th anniversary of D-Day, President Ronald Reagan delivers a speech at Point du Hoc overlooking Omaha Beach. He honors the Rangers who scaled the cliffs, the infantrymen who crossed the beach under fire, the paratroopers who jumped into darkness. The speech mentions overwhelming Allied air superiority and devastating preliminary bombardment. Louis Jörg has been dead for 22 years. His name is not mentioned. In the audience, a 73-year-old veteran named Robert Walsh, son of the bombardier David Walsh, who dropped those first fuse-equipped bombs on D-Day morning, listens to the speech. His father passed away in 1978, but before he died, he told his son about a Swiss watchmaker whose invention changed everything. "Remember his name," David Walsh had said. "Jörg, Louis Jörg. He saved thousands of lives, and nobody will ever know." The waves crash against Normandy's beaches, the same sound they made 40 years ago when landing craft approached through the pre-dawn darkness. The concrete bunkers still stand, silent monuments to Hitler's failed fortress. But the defensive networks that should have made Omaha Beach impregnable were shattered by precisely timed airbursts, designed by a civilian who never wore a uniform, manufactured by factory workers who never fired a shot, and delivered by bombardiers who never saw the faces of the men they saved. This is how wars are truly won, not just by courage under fire, but by the accumulated precision of unknown hands working in distant factories, solving problems that most people will never understand, creating technologies that history forgets even as it remembers the battles they made possible. Louis Jörg's workshop in Highland Park was demolished in 1987 to make room for a shopping center. No plaque marks the location. But somewhere in a military archive, a yellowed document records the production total: 2,187,000 M139 time delay fuses manufactured between 1943 and 1945. Each one built by hands that history forgot. Each one proof that sometimes the difference between victory and defeat is measured in thousandths of an inch.